Traditional convolutional neural networks, or CNNs, are not robust to certain symmetry transformations, such as rotation. Group equivariant CNNs, or GCNNs, generalize well to a variety of transformations, including arbitrary rotations, but have been too complex to implement on a phone. Now, for the first time, Qualcomm AI research introduces GCNNs running real-time on a phone. To make this possible on power-constrained edge devices, we made several optimizations, such as selecting a lightweight GCNN architecture and applying state-of-the-art quantization techniques. We also employ angularly band-limited filters and an additional loss, which reduces angular aliasing when using sparse filters. Both models were trained on the same dataset. Our demo showcases how a GCNN performs better than a traditional CNN, using a segmentation mapping task as an example on phones powered by the latest Qualcomm Snapdragon processor. The task is to correctly classify each pixel of lymph node scan sections as benign or malignant. Green highlighted areas show lymph node tissue that is considered malignant, while the areas without overlays are considered benign. The size and shape of the malignant cells, as well as their nuclei, are often abnormal, while benign cells tend to have the same size and shape. Specialized and experienced doctors typically make this determination. In our demo, the color of the highlighted segmentation overlay shows the accuracy of the model. A true positive is green, while a false negative is red, and a false positive is yellow. A fully accurate model would show only a green overlay with no red or yellow. Since tissue has no inherent orientation, we slowly rotate the images of the scans in 10-degree increments. Once a scan has been rotated by more than 360 degrees, we move to the next scan. Our side-by-side comparison shows a GCNN on top and the conventional CNN on bottom. The left image on each phone is the rotating tissue scan and corresponding output segmentation mask. The right image on each phone is a stabilized version of each rendered scan. This indicates how the segmentation mask varies with rotation. As the image rotates, the output of the conventional CNN deforms and changes unpredictably. For the GCNN, the output rotates together with the input and maintains its structure, resulting in a more accurate, stable, and robust classification. The enhanced accuracy of GCNN is demonstrated by its overlays being mostly green and matching the ground truth. The Jacques score calculates the similarity between the ground truth and model prediction. The graph of Jacques score at all rotation points shows that the GCNN is both more accurate and more stable. You can also see that quantized GCNN model retains accuracy very well. Several tools and SDKs were used in the development of this demo, such as the AI Model Efficiency Toolkit, or AMET, the Qualcomm Neural Processing SDK, and the E2 Equivariant CNNs library for PyTorch. Taking advantage of symmetries in neural networks is clearly beneficial. Equivariant CNNs are compute efficient, data efficient, and offer robust performance. Equivariant CNNs will enhance many diverse applications, from medical diagnosis to drones and autonomous driving. Our research will continue to push the limits of what's possible with artificial intelligence.